right, so we're going to start with this bell ringer today. Find the exponential function that passes through these 2 points. So this is what we did yesterday. So let's just get into it. So we have an exponential function in the form y equals ab to the x. And it's going to go through y equals 6 when x equals -2, and y equals 1 when x equals 1. Okay, so we can just solve this by substitution. So let's get a by itself, and the easiest one to get a by itself would be the red one. So we're going to have a equals 1 over b because we just divide both sides by b. So we're going to remember that and bring it over here and plug it in for a. And so we're going to get 6 equals 1 over b times b to the -2. Now what is b to the -2? It's 1 over b squared. So we have 6 equals 1 over b times 1 over b squared. So we have 6 equals 1 over b cubed. Okay, and so then we have to get b by itself. We have to figure out what b is. So we multiply both sides by b cubed, and we get 6b cubed equals 1. We divide both sides by 6, and we get b cubed equals 1/6. We take the cube root, so we get b equals 1/6 to the 1/3, which is going to be just some weird decimal. 1/6 to the 1/3. Okay, so it's just some crazy decimal. So we store that in your calculator as b, okay? And then a is 1 over that number. Okay, so we end up with y equals, let's see, 1 over 0.55 times 0.55 to the x, and you're going to be tempted again to multiply those two 0.55s together. You can't do that because exponents are stronger than multiplication, so they take precedence. We have to do the exponent first. And so this is your function. And so say we wanted to evaluate this when x equals 4, we could just take our value that we stored, and we're going to raise it to the 4th power, and then multiply it by 1 divided by that number. We have it stored, so it's really easy, and we'd get out 1.667%. And so yeah, there it is, that easy. Okay, so today we're going to talk about graphing the parent functions for exponentials, and we're going to talk about transformations. So the first thing we're going to do is we're going to go to Desmos. I'm going to close this out, and I'm going to show you this. So y equals ab to the x plus h. No, I want the plus h up there. So plus k. No, I want the h up there. Plus, no. It doesn't want to let me do x plus h. Okay. There we go. I'm like, I just did this a minute ago. Okay, so I did that really quick, but you notice I pushed the button all sliders, add all sliders, because what I wanted to do is I wanted to add sliders for all of these. So I put in values A, B, H, and K. And what Desmos said is like, wait a minute, those aren't normally variables. Those aren't like an X or a Y. So it asked, do I want to add sliders to it? And I said yes, because see, the cool thing about a slider is that you can change the value of B and it will change the function. So I don't have to put in, like, I don't have to keep changing the value of b. I can just use the slider. Okay, so first thing I want you to notice is when b equals 1, when everything equals 1, what does this graph look like? And actually, let's do h and k equal to 0, because h and k we know are shifts left and right for h and shifts up and down for k. So let's get rid of all the shifts, and we're just kind of into a parent function of this is basically y equals 1 to the x. What does it look like? Well, it's a straight line, and this is why we can't do 1 for an exponential, because 1 to anything is just 1. So let's change b. so that it's not 1. So when we change it so that it's bigger than 1, remember this would be growth, right? So it's going to start out slow, really, really slow. It's growing, 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 and then all of a sudden it starts growing faster. Now if we change b this way, you'll notice that we get to decay. So this is, again, we can't have 0 or negative numbers, so that's why it stopped there. This is decaying, which means it's starting out big and getting smaller. Okay, so let's look at a growth function. So here we have, let's see, b equals 3. Actually, let's do 2 because that's one we talk about a lot. It's doubling. Now what I want you to notice is when I'm moving this b, there's one point that never changes ever. Okay, do you notice? That doesn't matter what I change b to, that there's a single point that all of them all go through, even the decay ones. Every single one of them go through that point. Do you notice it's this point right here? This is the point 0, 1. And basically, it makes sense because anything to the 0 equals 1. Anything, right? If we take any function and we double it 0 times or triple it 0 times, we're going to get 1. Okay, so this one is 1. 0, 1. Every single function goes through it. And then even now, if I change my a, it's going to change that value because it's going to multiply all my x values by that. Okay, but if my a value, if it's not stretched, if I'm just at a parent function, it's going to always go through that point. Now, here's the interesting thing. Exponentials have tons of parent functions. In fact, you can have 2 to the x, 5 to the x, 1.5 to the x. So we could have e to the x. Oh, look, e. It just put in e. And it still goes through that same point because e to the 0 is still 1. But we can have all these different bases for b. So we can do that, and then let's give ourselves a b slider again. Okay, so we're going to slide b, and let's do it as a doubling. So we're going to do it as a 2 to the x. So our parent functions can all look like this. They're all going to look a little differently. But if you look at this, okay, when x equals 1, y equals 2, right? Because 2 times itself 1 time is 2. Then x equals 2, y equals 4. And then when x equals 3, that would be 2 cubed, which is 8. Okay, so the pattern for the exponential functions is defined by its parent function. Okay, so now let's see what happens when I change a. Actually, yeah, let's change a first. Okay, so we're changing a, and remember a is outside the function. Do you see it's not with the x? So the function is some number to an exponent. That's the function. And since a is outside of that function, it only changes our y values. Okay, it only affects our y values, not our x values. And it's going to multiply all of our y values by a. So if I change it up to 2, it's going to multiply all my x values, or excuse me, all my y values by 2. So now that point that was at 0, 1 is now at 0, 2. Okay, because if I start out with 2 bacteria and I double them 0 times, I still have 2 bacteria, right? Now, what if I start out with 1 bacteria and or 2 bacteria, sorry. What if I start out with 2 bacteria and I double it 1 time? Well, now I have 4. Okay, what happens if I start out with 2 bacteria and I double it 3 times, or 2 times, excuse me. This is 2. So I have 2 bacteria and I double it twice, it becomes 4 and then becomes 8. Okay, so it hopefully is making sense. So this a value is just going to basically multiply all of your your y values by that number. Okay, and again, because that's your starting value, that's when you've haven't grown or decayed it at all. That's how much it's equal to. Okay, and now these ones have a little bit more to do with, say, like shifting time than they do actual like application. But remember, if this h is inside the function, okay, it's inside the function with x, which means it's going to affect our x values, and it's going to shift them left or right. And remember, your x is a liar. So what looks like, if I have a positive 2 here, it looks like I should go to the right 2, right? But I don't. I actually go to the left 2 because x lies. So this h is going to shift it left and right. And then the k is going to shift it up and down. So you can graph any function by starting out with the parent function and then just looking at the all of the different transformations. So basically the idea here is we have the parent function. The parent function of this is just b to the x because there's lots of parent functions. They all look just slightly different. You can have 2 to the x, 5 to the x, 10 to the x, e to the x, all of those. Okay, so our parent function is just b to the x. So in our parent function, what is their y-intercept? They always have a y-intercept of 0, 1. Okay, if we haven't shifted or transformed it at all. Now we could write this as y equals a b to the x plus h, just like we had it there in Desmos, plus k, so we can talk about what each of those do to it. So if we haven't transformed it at all, we have a y-intercept of 0, 1. We do not have an x-intercept, right? Because we have an asymptote. So if we haven't transformed the function at all, we have no x-intercept, but we do have an asymptote at y equals 0. We have a horizontal asymptote at y equals 0. Now, what in this would define our horizontal shift? Well, our horizontal shift is negative h, right? It's the opposite of whatever we see for h. So that's going to move it left and right. And of course, that's going to affect our y-intercept, right? And then vertical shift is k. Remember, y is not a liar, so it goes with exactly what it looks like. So that's going to shift it up and down. And again, that's going to shift our asymptote, right? So if my k value is 3, I'm going to take my asymptote here at 0, and I'm going to move it up 3, and now my asymptote is at whatever k is, right? My asymptote is at whatever k is. And I'm not going to say that we have to like always, you don't memorize asymptote equals k, but what you might want to know is that, you know, your asymptote starts at 0 and it shifts up to k, okay? Our vertical stretch is a. How do we know if it's growth or decay? Well, if b is greater than 1, it's growth. And if b is in between 0 and 1, 0 is less than b is less than 1, then it's going to be decay. Okay, now what's the domain and range? What numbers can I put into here? Well, I can raise a number to any power, right? Like there's no restriction. I can put negative numbers, I can put fractions. We've seen lots of fractions, we've seen lots of things. So my domain is all real numbers. I can put literally any number in here I want and it's totally legal. But the question is, what do I get out? What do I get out? And if you think about all exponential functions, they're going to look like this or like this, right? If they're decay. What do I get out? Well, I have an asymptote at 0, and they never goes below 0, right? Like, unless we shift them, our function has to stay positive because there's no way you can put any number into an exponential and get out a negative number. You can't be like, oh, b to the negative 5 is negative. Nope, it isn't. It's still positive. It's just 1 over b to the 5th. Okay, so our range for our untransformed, which is really what all of these are, would be y has to be greater than 0. It can't be equal to 0. So let's just hurry. We've got a minute and a half for me to graph a couple of these for you. So here is my graph. So what's the parent function here? The parent function is 2 to the x. So I'm going to go ahead and graph that. It goes through 0, 1. It has an asymptote at 0. And when x equals 1, y equals 2. So there's my parent function. Now the 3 causes it to multiply everything by 3. So now I'm going to go, this is going to be a 3 and this is going to be a 6. And so it's going to kind of go like this. But my asymptote, when I multiply 0 by 3, it's still just 0. Okay, but this 2 is positive, so it's going to shift it to the right 2. So we're going to go 1, 2 right here. And then this 1 is negative, so we're going to go down 1. So we're going to go right 2, down 1. And so our asymptote shifted down 1, so we'd have a new asymptote down here. And we have a graph just like that. It's not perfect. We can do better ones, but I'm running out of time. So there you go. That's the idea behind graphing exponential functions.